Hello, this is section 2.5 on the concept of continuity of a function at a point A. This is from the James Stewart Calculus Early Transcendentals book, and here's the definition of a function being continuous at a number A. A function is continuous at a number A if the limit as x approaches A of f of x actually equals the function output, f of A. To determine that, we have to make sure that the function satisfies the three following conditions at A. In other words, f of A has to be defined. And what does defined mean? That means f of A is a real number. It's a finite number. In other words, there's no zeros. It doesn't have zero in the denominator. We don't have negative numbers underneath radicals, etc. So we actually have a defined finite number. F of A has an output. A is part of the domain of the function of x. Also, we have to have that the limit as x approaches A of f of x has to exist as well. So what does it mean for the limit to exist? The limit is not equal to positive infinity, it is not equal to negative infinity, and it is not equal to it does not exist, where the limit from the left does not equal the limit from the right. Good? So, in other words, the limit is a finite real number. In the same way that the f of A is a real number, and that really unifies. The third one is that those two values have to be the same. The limit as x approaches A of f of x actually has to equal the function output, and that's when you can conclude that a function is continuous at the point A. So we're going to go through and verify or determine if a function is continuous at a particular value of A. And usually you'll get some piecewise defined functions here to determine that, or you might be given a graph. So let's look at that. So here we've got this f of x equal to x squared minus 1 over x minus 1 if x is not equal to 1, and 3 if f is actually equal to 1. Now we can go ahead and graph it and determine if this is the case, or we can take our limits. So we can start with number 1. What is f of A? That's going to be f of 1. And if we look at our piecewise defined function, that's going to be equal to 3. Okay. Now in all other instances, when A is not equal to 1, it's going to equal that function output, and or the function x squared minus 1 over x minus 1. So I'm going to see if that limit exists. So I'm going to say as the limit as x approaches 1 of f of x is going to equal the limit as x approaches 1 of x squared minus 1 over x minus 1. And remember, when calculating limits, we go and try to evaluate at that point, and we end up with 0 over 0. So that tells us that 1 is a factor of the denominator and also a 0 of the numerator, or x minus 1 is a factor of both. So we learn to manipulate, and we factor the numerator, we factor the denominator, and we cancel the factor of x minus 1 because we know that 1 is a 0, and we end up with the limit as x approaches 1 of x plus 1, and we begin our limit calculation again, and that's going to go to 1 plus 1, which is 2. So we have determined that the limit as x approaches 1 of f of x is actually equal to 2. So we go back to the final criteria for a function to be continuous, and we ask ourselves, does the limit as x approaches 1 of f of x actually equal f of 1? And if we go back to step 1 and 2, we're asking ourselves, does 2 equal 3? And our answer is no, so we violate step 3, or criteria 3, And so our conclusion, which these little 3 dots means therefore, f of x is not continuous or discontinuous at a equal to 1. Good. We're going to do this here. We're going to follow the same 3 steps, and we'll say 1. What is the value of f of 1? The value of f of 1 is 1 over 1 minus 1 squared, which is 1 over 0, and that is undefined. We can finish right now, and we can just say conclusion. F of x is not continuous at x equal to 1. Good. Here are some illustrations that of particular graphs that might convince you of those 3 criteria that need to be met in order for a function to be continuous at a particular value of a. And remember, continuity is if your collection of points is fluid. Think about graphing that function. If you ever have to lift your pencil up from the graph to finish graphing, then you know that you've got a problem point. Or if you have any vertical asymptotes, you will have a point of discontinuity. So in this case, in the very first one, we have here, yes, the limit as x approaches a exists because the 2-sided limit outputs are approaching that value there. However, f of a does not exist because we have that open hole. So that violates the very criteria of the first one. The second one, we have that f of a exists. The limit as x approaches a exists, but the limit as x approaches a of f of x does not equal f of a, right? Because we have an open hole. This is the limit where the open hole is because the function outputs are approaching that from both sides. But this is actually f of a, and that is different from the limit. And if you went to graph that function, you would graph the first part to the left of that hole, create a hole, lift your pencil up, draw the output at f of a, and then go back to the hole and continue graphing. And so it's not continuous at x equal to a. Here in the third one down here, we have that f of a exists because this is our f of a, right? So f of a exists, but the limit as x approaches a, which is a 2-sided limit of f of x, does not exist because the limit from the left is where the open circle is and does not equal the limit from the right where the function output is. You will learn in the next 10 minutes or so that this function is continuous from the right because it follows the 3 criteria for limits from the right, but it is not a 2-sided continuity, and so it's not continuous really at x equal to a. It's only continuous from the right. And then the final one is we have that f of a does not exist. Right, we have no output on a vertical asymptote. Because the limit as x approaches a of f of x, that 2-sided limit is positive infinity, but infinity does not exist. So it kind of violates both of the first 2 criteria. Okay, so what are right and left continuity on an interval? So again, the definition here, a function is continuous from the right at a number a if the limit as x approaches a from the right is actually equal to f of a. And this is what I was talking about in this particular scenario. This is the limit from the right, and the function outputs are approaching f of a, and it actually equals f of a, so this function is continuous from the right. So the same criteria holds, the same 3. The f of a has to exist, the limit from the right has to exist, and they actually have to equal. So that third criteria really is the main event of those three criteria. And similarly, the function is continuous from the left at a if the limit as x approaches a from the left actually equals f of a. Okay, so here we'll just have some random function here. This is a function that does pass the vertical line test. Again, the open holes represent limits there, or you can, but really the output of the functions are the solid dots. Good. So what's the question here? It says, at what values is x discontinuous, and justify your answers. So this is our function g of x here from -3 to 3. I see that there's no function output here, so at x equal to -2, and what's the justification? And that is that f of -2 does not exist. And for the sake of continuing, I'm going to say DNE for does not exist. Good. It's also discontinuous at x equal to -1. And what's the justification there? The two-sided limit, the limit as x approaches -1 of g of x does not exist. And why does it not exist? It does not exist because the limit from the left is this value and the limit from the right is this value, and they are not equal. So they do not, the two-sided limit does not exist. At x equal to 0, we have a discontinuity because we do see a jump. And at x equal to 0, we do have that, the final one is that the limit as x approaches 0 of g of x does not equal g of 0, right? G of 0 is equal to 2, and the limit as x approaches 0 of g of x is equal to 1, right? We have the limit from the left equals the limit from the right, so the limit exists and it's equal to 1, but this is the function output of g of 0, and it is not equal, so they are discontinuous. Is that helpful? Hopefully that's helpful. And then we also have that it is discontinuous at x equal to 1. And why is that? We do have that g of x does have an output, because that g of x is this output, it does equal 1, but the limit as x approaches 1 of g of x does not exist. Okay, and that is because the limit from the left is 1, but the limit from the right is infinity. Okay. Okay, so for the values found in part A, which are right continuous and which are left continuous. Okay, so the right continuous are do I have anything from the right that is continuous? So if I'm going to go from the right, if I'm just going to look at x equal to 1, the limit as x approaches 1 goes to infinity. So that limit does not exist, and so it's not continuous from the right at x equal to 1. From the right here, if I go to 0, going from the right, the limit is 1, but the function output is 2, so it's not continuous at x equal to 0. Going to -1 at those points, the point of continuity, which are of the values found, okay, because I was going to say it's continuous where we do have function outputs. But looking at x equal to -1, my limit is going to be 0, but my function output is going to be 1. And so I'm going to say no points. And at x equal to 2, we have no function output at x equal to -2, so no values are right continuous. All right. Now I'm going to go limits from the left, that's limits below, and which ones are left continuous. And I'm still looking at these values, x equal to -2, x equal to -1, x equal to 0, and x equal to 1. It's not at x equal to -2 because we have no function output. F of -2 does not exist, so automatically we don't have any output. It's automatically not continuous. Okay. Also, any vertical asymptote, not continuous at that point either because the limit does not exist at that value. So 1 and -2 are out of it. But at x equal to -1, we do have that the function outputs approach 1. The function output is approach 1, and the function output at -1 is 1, so it is continuous because the limit as x approaches -1 from the left of g of x does equal f of minus, or does equal g of -1, sorry. It's also continuous, it's not continuous from the left at 0 because the limit from the left is equal to 1, but the function output is equal to 2, so it is not continuous from the left at 0. And again, at 1, it is not either because we do have, well, from the left it is continuous because if I take my function outputs from the left at 1, it does equal, so it is continuous from the left, but it's not double continuous because we do have an asymptote there because the two-sided limit does not exist. And this is because the limit as x approaches 1 from the left of g of x does equal the function output there. And hopefully that is helpful in that analytic geometry. Okay. And then finally in part C it says list the intervals at which this function is continuous. It didn't say right continuous. It did not say left continuous. It said continuous, so that is two-sided continuous. So if I go back to these points of discontinuity up here, I take these values and I want to exclude them from the entire real number line. So if I just write the entire real number line, and I have infinity and minus infinity, I'm going to get rid of -2. I'm going to get rid of -1. I'm going to get rid of 0. And I'm going to get rid of 1 because those are our points of discontinuity, right? And we did that from part A. And so I want to put open circles there. Good, because that's another criteria. And then I just want to calculate their intervals. So what is the interval from minus infinity to -2? We're going to go from minus infinity, open, a rounded interval. We want to go from -2 to -1. And we want to go from -1 to 0. And we don't include them, that's why we don't have square brackets. We want to go from 0 to 1. And then we want to go from 1 to infinity, right? Those are the intervals where we do have function output. So wherever you see like solid lines, you'll know that they're continuous at all of those points in there. Okay. We do want to skip ahead just for shortness of time to not make this video too long. The continuity rules are the function, if f is continuous and g is continuous, then f plus g is also going to be continuous. F minus g is going to be continuous at a constant times that function is going to be continuous. The product of continuous functions is continuous. And the quotient of those continuous functions is also continuous provided that g of a is not equal to 0, right? If we get a 0 in the denominator, it would violate the very first criteria, which is f of a has to exist, or that new function h of a would have to exist. And since g of a would give it 0, it wouldn't. Okay? Any polynomial, that's going to be continuous everywhere. It's going to be continuous at all real numbers. It never gives you a 0 in the denominator. It doesn't have any radicals, and so it's going to be continuous everywhere. every rational function that's a polynomial over a polynomial is going to be continuous everywhere it is defined. And how is that defined? That means everywhere except where at values that make the denominator equal to 0. Okay, so here, determine all intervals where the function is continuous. In this case, this is a polynomial, so we're just going to say from minus infinity to infinity. Determine all intervals where the function is continuous of this second function, and it's where at all x where the denominator does not equal 0, because we have to have f of a has to exist and we can't divide by 0. So we want to plug in x squared minus 3x plus 2 can't be equal to 0. If we use the factor property, you can also use the quadratic formula if you would like. This is x minus 2 times x minus 1 can't be equal to 0. So that means x minus 2 can't be equal to 0, and x minus 1 can't be equal to 0. So x can't be equal to 2, and x can't be equal to 1. If you're going to write the intervals, then again, we'll want to graph those points of discontinuity on your number line. And if I have 1 and I have 2, this is going to be an open hole. This is going to be an open hole. And so this interval in here is going to be minus infinity up to 1. Open rounded interval notation, not square, because square would mean that 1 would be included. We would have 1 to 2, and then we would have 2 to infinity. Good. And that would be our answer. Those are the intervals where our function is continuous. Okay. In general, so another theorem is that if a continuous function has an inverse, remember it has an inverse if it is 1 to 1. In other words, if your function passes the vertical line test, it is a function. But if your function also passes the horizontal line test, then it has an inverse. And that inverse is also going to be continuous. So your trigonometric and exponential functions have no breaks or gaps on their domains. Okay. Also, these types of functions will be continuous at every number also in their domain. So polynomials are going to be continuous everywhere where it has a rational or has a real number output. Trigonometric functions where they have real number outputs. For example, secant is equal to 1 over cosine, right? So don't forget, secant theta is 1 over cosine theta, and cosine is not is equal to 0 at odd multiples of pi over 2. So at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. Notice that that's not continuous at theta equal to pi over 2, for example. Good. Exponential functions everywhere. So everywhere where it has a real number output, they're going to be continuous there. So that kind of reinforces when you calculate your limits, your first approach. If you're going the limit as x approaches a, your very first approach is to substitute the value a into your f of x. And if you get a real number output, that is your limit, and it's going to be continuous there. Good. All right. Use continuity to evaluate the following limits. So again, right? So if I say the limit as t approaches pi over 2 of cosine of t, this is going to go to cosine of pi over 2, and cosine of pi over 2 is equal to 0. Just because it's 0 doesn't mean it doesn't exist. 0 is a real number. It's the dividing line between positive and negative numbers. It's one of the most important numbers out there, so it's only division by 0 where you have a problem. Here, if I just go ahead and plug in my value, t equal to minus 1 of t squared. Oh, I've already got it listed there, so why am I writing it out? I'm just going to go, this is going to go to minus 1 squared minus 1 over minus 1 squared plus 1. I get 1 minus 1 over 1 plus 1. I get 0 over 2, and that's still equal to 0, and it is defined, and that is our limit. Good. And we can use continuity because it is defined here, right? F of minus 1 does equal 0, and the limit from the left does equal the limit. We can go ahead and use the function output. Determine all values where f of x is equal to this piecewise defined function is discontinuous. If discontinuous at a point, determine if the continuity is left continuous, right continuous, or neither. Sketch a graph of f to verify your answer. Maybe I'll have time to sketch, maybe I won't. But which of the problem points do we have? We actually want to look at x equal to 2 because that's a break off where we're going to change the shape of the graph, and also at x equal to 4 because that's another place where we're going to break off. Good. So at x equal to 2, what is f of 2? Right? And f of 2, we see that it's x bigger than or equal to 2. This is going to be 2 plus 2, which is equal to 4, right? Because we have that f of x is equal to x plus 2 when x is equal to 2. Good. Now we want to evaluate the right-hand limit and the left-hand limit. Good. So what is the limit as x approaches 2 from the left of f of x? That means when x is less than 2. Then this is going to be the limit as x approaches 2 from the left of 2 to the x, because that's what f of x equals when x is less than 2. And then that is going to go to 2 to the 2, which is equal to 4. Good? So I do see right now that because the limit as x approaches 2 from the left of f of x actually equals f of 2, it is left continuous. F of x is left continuous at x equal to 2. Good, so we'll have a connection there. We won't be lifting our pencil, we'll just be changing the shape of the graph. But I still need to determine if the two-sided limit, if it's quote-unquote continuous, not just necessarily right or left. So what is the limit as x approaches 2 from the right of f of x? We're only concerned with the values that are very, very close to 2 and not necessarily those bigger than 4, right? So our limit as x, and that goes back to the precise definition of the limit. So we're going to use x plus 2 here for f of x because those values between 2 and 4 are closer to 2 than the values for square root of x minus 4, which would be for values bigger than 4. So what is this? The limit as x approaches 2 from the right is going to go to 2 plus 2, which is also equal to 4. And so because the limit as x approaches 2 from the right of f of x also equals f of 2, it is right continuous at 2. And because it's right continuous and left continuous, it's continuous. So we can say, therefore, since the limit as x approaches 2 of f of x exists and it equals 4, and that also equals f of 2, then f of x is continuous at x equal to 2. So the other problem point is x equal to 4, and we'll complete that as well. So what is f of 4? F of 4 is going to be the square root of 4 minus 4, because that's where we have, in our definition, when x is equal to 4, we use square root of x minus 4. And that's going to be the square root of 0, which is 0. Okay. What is the limit as x approaches 4 from the left? And if I'm coming from the left, then I'm coming from below 4. And that's going to be the limit as x approaches 4 of x plus 2. And that's going to give me 4 plus 2, which is going to give me 6. So automatically, I can say that f of x is not continuous at x equal to 4, and it's not left continuous. It's not continuous and not left continuous at x equal to 4, because the two-sided limit won't be true, because the function output does not, the limit won't equal the function output. Good? So, but I want to still test if it's right continuous. Good? So the limit as x approaches 4 from the right of f of x, and that is actually equal to, from the right is going to be for values that are bigger than 4, and I still get, this is going to be equal to the limit as x approaches 4 from the right, and that function is square root of x minus 4. That's going to 4 minus 4, which is square root 0, which is 0. And since the limit as x approaches 4 from the right of f of x equals 0, which also equals f of 4, we conclude that it is, or f is right continuous at least, but it's not two-sided or left continuous. It's not continuous and it's not left continuous. But it is right continuous at x equal to 4. Good. All right. Sometimes we want to find where we can extend our functions to be continuous at a value. So we're still going back to those three criteria. So it says here, find a number k such that f is continuous. Okay, so we are still using, and what is our problem point? Our problem point is x equal to 2, right? Because we've got a shift in our graph. We know that x squared is a polynomial, so for all points it's going to be continuous, but we're switching the graph when we get to kx. K is a constant. That's also going to be a line, and that line, it's still a polynomial. It's just a linear polynomial. That's also continuous at the other values, but again, we split. But how can we ensure that they're going to be continuous? So we first calculate, we want to make sure that the first criteria works. What is f of 2? F of 2, according to this, is going to be 2 squared, which is going to be 4. What is the limit as x approaches 2 from the left? The limit as x approaches 2 from the left of f of x is going to be the limit as x approaches 2 of x squared, because that's the value, or that's the function expression for values less than 2, and that's going to equal 4, so that works. But what's the limit as x approaches 2 from the right of f of x? That's going to be the limit as x approaches 2 from the right of k times x, and we want it to equal 4, right? So, but what do we do when we calculate limits? Our first approach is to substitute our value. So we want 2 times x to equal 4, or 2 times k to equal 4. And so now we can solve for k. And k here is going to be 4 divided by 2, which is 2. So for k equal to 2, f of x will be continuous at x equal to 2 and all other values of x. Good. All right. I will stop here and maybe create another video in terms of limits of compositions of functions and talking about continuity of a composition of functions, because I don't want this video to go too long.